Hey guys, this is our second last unit. We're getting into curve sketching, and I just wanted to tell you the difference between, the previous couple units and then this unit. So the previous couple units, you'd been looking at derivatives in an algebraic sense, and now you're going to be looking at it from a graphical sense. So what does first derivative and second derivative actually mean about a graph, like an original function? We kind of touched upon it, but we're going to delve into it a lot deeper. Okay, so this lesson is going to be on increasing and decreasing intervals and local extrema, and all of that has to do with our first derivatives. So let's get started because we got a lot to cover. A function is considered increasing when you start off at a certain part on the function. So I have my function in black, and I'm going to start at the pink dot. We're going to travel towards the right-hand side, and so we'll get another dot on the function. If from the left, going towards the right, you go up, or in other words, you have a positive slope, or in other words, again, your derivative, like your first derivative, because you guys know what that means, slope, is positive, that means that your overall function is going to be increasing. So one more time, your derivative does tell you something about your original function. So if your derivative is positive, your original function must be increasing. Now going into the opposite, which is not increasing again, you didn't see that, decreasing. So you're starting at a point on the original function, going towards another point a little bit to the right. If it goes down, then that means that you have a negative slope. Your first derivative is less than 0. If you have a first derivative less than 0, then that means that your function is decreasing within that region. Okay, so if you want to test for intervals of increase or decrease, just to summarize, you would then have to take the first derivative, and if your first derivative is positive, that means your original function is increasing. If it's decreasing, then that means your first derivative was a negative number. Okay, so let's take a look at that graphically and see if we can figure this out. Example number 1, determine the intervals of increase and decrease. So we had already talked about it before that to find the intervals of increase and decrease, you're going to have to take the derivative, right, for each one. But if it's greater than 0, that means you're increasing. If it's less than 0, that means you're decreasing. So what happens if it is exactly 0? Well, that means that you're not increasing or decreasing. You're just flat, right? So we had talked about those peaks before, and at each of the peaks, you're going to have a slope of 0, exactly 0. Okay, so this is where f at x, x prime, f prime at x equals to 0, and f prime at x is also equal to 0 here. So the first one looks like it has an x value of negative 1.5, let's just say. And then your second peak has maybe a 4.5 x value. These two numbers are pretty important. They divide up your graph into certain regions. Okay, so let's reiterate. At exactly those x values, your slope is 0. But to the left or to the right of those x values, you have an increase or decrease. Okay, so let's talk about increases first. Where is a graph a positive slope? So all along here, you're going to have positive slopes of varying degrees, but all of them are going to be positive. And so you're going to be increasing when x is anything from negative infinity all the way to negative 1.5, but not including 1.5. So we put the round bracket because at exactly 1.5, you have a slope of 0. So that doesn't really count if it's just greater than 0. Okay, we also have this side of the curve. So any of the slopes on this side of your curve going from left to right are all going to be positives as well. So also include negative 1 point, no, what am I doing? Okay, also include 4.5 to infinity. And again, round brackets because you're not including the 4.5. At 4.5, you have a slope of 0. Okay, now we're going to talk about decreasing. So I think you can kind of figure it out. Negative slope is happening in the middle from left to right. Okay, so decreasing is anywhere from negative 1.5 to 4.5. All right, so that's how we can figure out intervals of increase through a graph. But what if they gave it to us algebraically? Like they told us, okay, find the intervals of increase and decrease, but you got to do it algebraically. So it's not a problem. We just do the exact same thing, except we just won't be drawing it. Okay, so we have to take the derivative, and you guys know again, the derivative is going to be greater than 0 here, and the derivative is going to be less than 0 here. Okay, so first we need the derivative, and you guys know how to do that already. So I took the derivative, and I want to know where the special numbers, where my boundary lines are going to like appear. And so that is when it equals to 0, because remember, those are the peaks. This gives you your max and mins. Okay, so those peaks. And those peaks are important because they break up the graph into the positive and negative regions, so the increasing and decreasing regions. That means that you should set this equal to 0 and start to solve for x. Okay, so I'm going to assume that you guys know how to do this step because you guys have gone through advanced functions. So breaking up that cubic into factored form in order to find the x-intercepts for your f prime at x graph. Okay, so this is going to be negative 1, this one's going to be positive 2, and this one's going to be 4. What do those actually mean? Okay, for like 2 seconds, I'm just going to talk about graphing. You know that this guy is a positive leading coefficient for a quartic. And so we're probably expecting some sort of shape like this, right? And so how many peaks do you see? Well, there's 1, 2, 3 max and mins. Those are all going to have a slope of 0. So that's where this guy, and this guy come in. This is where it's probably x equals to negative 1. This one's probably where it equals to 2. And this one's probably where it equals to 4. So that's why when we make our interval chart, which is our second step, right here in between negative infinity to 2, we're going to put our x equals to negative 1. Okay, but notice that again, we have round brackets because we don't want to include it, because that's where we're going to have a slope of 0. Same with this guy, is going to be x equals to 2, and this one x equals to 4. So those numbers are pretty important because they give us each of the regions that make up our boundaries. Now we just do the first derivative test. So we do the interval chart. I'm going to talk about a first derivative test a little bit later, but essentially what we do is take our first derivative function, break it up into pieces. Really the most important one is down here. But we break it up into pieces to make it a little bit easier in order to figure out if it's a positive or negative within that region. Okay, so within the negative infinity to negative 1 domain, I don't know, choose like negative 100 and sub it in and you'll just get these. Okay, so it's going to be negative. Maybe in the next domain you would pick 0, and so if you sub in 0, you're going to get something like this. And again, I'm going pretty fast because I assume that you guys have this knowledge already. Okay, and the next one you would maybe pick 3 and then sub in a 3 into each of the brackets and get their symbols. And then the last one is usually almost always positives because you pick like a huge number like 1,000. Okay, so what did that actually tell us? Let me scroll up a little bit, just a tad. In our original function, we have increasing happening here. So our original function will be increasing within negative 1 to 2 domain. It's also going to be increasing from 4 to infinity. But it's going to be decreasing from negative infinity to negative 1, and then also decreasing from 2 to 4. Okay? And we can write all of that down because we should probably put the increasing and decreasing. So I'm going to write that again. Therefore, it's going to be increasing. X belongs to negative 1 to 2 and 4 to infinity. And then we have decreasing. I mean, this is kind of like our therefore statement because that's what they asked us for, right? Oh, I got distracted because I was talking. I'm always talking. Negative 1 plus 2 to 4. Okay? This should make sense because didn't we say that it is a positive quartic function? That's what we basically found from doing the first derivative and using a first derivative chart, like a test. Okay? Now, if we were to graph the first derivative, what we would have is we would take this information and maybe say, okay, negative, positive, negative, positive. What does that actually mean in terms of the, not the original graph, but the f prime graph? All right, so now we're talking about f prime, not f at x. Okay, and you had negative 1, you also had 2, I believe, and also a 4. So remember how it was like negative, positive, negative, positive? These are our domains. Okay, and it's going to go like this. Coming in from negative y values. Positive. Underneath is negative again. Positive. So anything in your positive y values is going to be your positives. Anything in the negative y values is going to be your negatives. And this should make sense because isn't this a cubic graph? Before we had a quartic, and you know that if you take the derivative of a quartic, you're going to get a cubic. So this is our cubic graph. Now the boundaries of increase and decrease, we have basically said, if you take the derivative and you set it equal to 0, you're going to get something called the local extrema. This is talking about your max and your mins. Okay, so basically we were saying the peaks. Right? And any of those numbers, so when you found your x values, they gave us those dotted lines that it was able to break up the graph into. We can also find like other critical numbers that will help us to figure out our boundaries. And so another one would be when f at x is undefined. And so any asymptotes are also considered critical numbers. All right, so let's try one together. Find the intervals of increase and decrease. I don't really want to graph this. Okay, so what I should first do is figure out any max and min, so any local extrema. All right, and I'm going to do that by setting this equal to 0. All right, so taking the derivative, and I'm going to do this super fast. I'm probably going to do a quotient rule, so something like this. All right, so there's your quotient rule, just super fast. You're going to set it equal to 0 in order to find the peaks. All right, now the critical numbers that we're going to use for our chart are going to be any x-intercepts here. Okay, so that would basically be when the top is equal to 0. Okay, so we look at our numerator in order to solve for when x equals to 0. Okay, so negative 2x equals to 0, and then that's going to be just 0. So you'll notice that I've already put that into my interval chart. All right, now you'll notice that you do have some sort of restriction in your denominator because I can't just take this, bring it to the other side through a multiplication, and all of it would disappear. So those are still like important numbers. We can't just get rid of them. So we'll just analyze them in terms of a vertical asymptote. So we know already that this x squared minus 1 squared can't equal to 0, right? Because if it does, you're going to have a denominator of 0, which is impossible. You're going to get an error. So let's start solving for it. We're going to square root both sides. Okay, so x squared minus 1 is 0. Okay, bring the 1 over. Oops, these should be cannot equal to, right? All right, and doing a Square root will leave you with a positive, negative, 1, and that's x can't equal those. So those are actually your vertical asymptotes at a formula. Now this is the equation, okay? So the equation of the vertical asymptote is x is negative 1 and another one, and x equals positive 1. Okay, so we have to include those here and also here. Technically, these are going to be asymptotes right along here. All right, so let's start analyzing the positives and negatives. So we're going to put numbers in. I'm just going to give you the answers. Okay, positive, 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 but you can check always if you'd like to by subbing in your own numbers. I make mistakes because I'm human. Okay, so there are your increases and decreases. So when it's a positive slope, your graph is going to be increasing. When it's a negative slope, your graph is going to be decreasing. All right, and we probably want to put that in terms of some sort of a therefore, because they asked us for the intervals of increase and decrease. So we would say it increases when x is negative infinity all the way to negative 1. So we're not including the negative 1 because there's an asymptote there. And from negative 1 to 0. And then decreasing when x is 0 to 1 and 1 to infinity. Okay, so far so good? All right, let's keep going. I just realized I don't have a step 2. I'm going to assume that that's probably my step 2. Okay, because my interval chart is my step 3. All right, let's talk about local extrema, which are my maximums and minimums. I'm going to hit you with a bunch of different words now. Okay? So any of these guys are called local maxes or mins, or local extrema. Extrema means you're going from like a positive slope to a negative slope, or a negative slope to a positive slope. So I'm just going to talk about, for now, a local maximum. Notice that your local maximum is when you go from a positive slope to a negative slope. Okay, so that's what they mean by this. Now, notice that for a local minimum, you're going from a negative slope to a positive slope. Now, all of these are called turning points. Turning points are the same as local extrema. When they're talking about how do I say this? It gets confusing with all of these different terms. I don't know why they need so many different words for the same thing. Okay, let's see if I can specify. Let's give you another piece of paper. Okay, let's say that you have a maximum, right? If you're talking about this guy right here, that is a turning, turning point. Now, at that turning point, you have a positive slope to a negative slope. So obviously, you guys know this already. That's going to be a maximum, which is a type of local extrema. Okay, now if I was talking about a minimum, all right, you still have your turning point. This is going from a negative slope to a positive slope, and therefore this is going to be a min, which is also a local extrema. You're going to be hit with another word a little bit later, which is critical points. And so I'm just going to tell you that critical numbers is referring to any important numbers. So important numbers would be anything that will give you your max or mins. Something called points of inflection, not intersection, inflection. Okay, any, say, asymptotes. All right, and then also I think the limits of your domain. You know when like they give you something like this, it's like, I want to talk about from here to here. So this and this would be the limit of your domain. So those are also important numbers. All of the critical numbers will be put into your interval charts. And so not all of those are actually called your turning points or your local extrema. They're just called very important numbers, which is why for some reason they're quote unquote critical. Oh, okay, so I hit you with it way faster than I thought. Unless I forgot something here. Did I forget something? Nope, I'm good. Okay. All right, so there you go, a critical number. Now you know what a critical number is. First derivatives test is basically where you do the chart. Doing the chart tells you where the domains are, where your derivatives are equal to 0, right? But when we take a derivative and we set it equal to 0, we don't know if it's a max or a min. And so we test it using all those positives and negatives, which we call the first derivative test, to tell me, okay, if it's going from like a negative to a positive, then it must be a min. If it's going from a positive to a negative, then it must be a max. If it's not really changing, then you don't really have either a max or a min. All right, so here we go. We're going to try some examples. Number 4, determine the local and absolute extrema for the function. Okay, so let's go into what an absolute extrema is. Going back to this diagram. Absolute means the very, very lowest. Notice that you have like minimums somewhere else, and we would call those local minimums. Okay, but this guy right here is the absolute minimum at the very lowest. It doesn't necessarily have to be, say, at a peak, because as you notice, it's just part of where the domain is from here all the way to here. And so this guy is the absolute maximum, but this one right here would be a local maximum. So we need to identify those ones as well if the question asks us to. Okay, so going back to the question that we were on, determine the local and absolute extrema. So they're looking for the local and absolute max and mins, which means that we should probably take the derivative. Okay, so first of all, take the derivative. Y prime is going to be negative 6x squared plus 18x. Okay, and we're going to set it equal to 0 in order to find those peaks. So I'm thinking I might want to like factor just a bit because it helps me to solve for x minus 3. Okay, so everything is nice and factored, and I can start like solving in each part. So this is going to give me an x value of 0. This guy's going to give me an x value of 3. And so those two critical numbers, those two critical values, are what I'm going to put here and here and break up that domain. All right, now round brackets on either side again. And so if I start to test by subbing in numbers into my f prime, I'm going to get a negative, a positive, and then a negative again, which is going to tell me that my graph goes decreasing, increasing, and then decreasing again. So let's now put in what we actually know. From negative infinity to 0, and then from 0 to 3, there is a local extrema happening, okay? And since it's going like this, that must mean it's a minimum. So we would actually write, there's probably a minimum happening here. Now that you have some sort of diagram in your head, that would probably be a maximum. And so we're just going to write, there's a maximum happening here. Now, if we wanted to know the actual coordinates, what we'd have to do is we'd have to take this x value, which is going to be 0. Why did I write that? I don't even know. I'm going to take 0 and then plug it into our original function. And so something like that would be the minimum point. So that would be also called our turning point. And then again, the same thing with the max. You can sub in a 3 into this equation, and then you would get the maximum point as well. I'm going to take a look further at the domain for a second. So negative 1 to 5. All right, let's see if we can find our absolute extrema. I took -1 right here and the 5, and I wanted to know where that was in terms of the graph. And so subbing that into the actual equation, I'm going to get something like 15 here, and then the domain, upper bound of my domain is going to be over here at 5. But I also wanted to see where my critical values, like what those numbers were. And so we already solved one of them, which was 4, because that's right there, right? And then when f was 3, I got a y value, sorry, if f at 3, so x equals to 3, I'm going to get a y value of 31. That means that the absolute maximum is going to be this guy. We call that an absolute max. So where's my absolute min, guys? Down here. Absolute minimum, because it's the smallest. The other two are going to be local maxes or mins. I don't know that this one is called a local max or min just because it's part of the domain. So if I sketch something like this, okay, you got -1, so maybe -1's right here. This is 0. 3 is probably over here, and then 5's here. So you're going to get up to 15. That means that there's a dot right there. Okay, 0, 4 might be somewhere around there. 3 and 31. So maybe if this is 30, might be up here somewhere. And then you also have 5 and -21. Okay, so maybe that's like all the way down there somewhere. So you're getting something that looks like, right? Do you see how like this is the absolute max, which is this guy? And this guy would be your absolute min, which is that guy. Anything in between, like this guy, would be just a local minimum. So let's go into the last part. Determine the local and absolute extrema for the function. Okay, so first, again, find the derivative, set it equal to 0, and then solve for any of your x values. Take that x value, put it into your chart, and then solve for the positives and negatives and see what happens to your original graph. Because this one is going from increasing to increasing, that just means it's continuing to increase. There's no turning point, there's no local extrema. Okay, now what I can do is I can test the upper and lower bounds of the domain. I do have an absolute minimum and an absolute max, but then I don't have any local extrema or turning points. Okay, so let's take a look at this one. Number 6. Determine the intervals of increase and decrease and any local extrema for a different function. So basically the same thing. Again, take the derivative, set it equal to 0. Okay, I'm sure you guys can pause this, by the way, and just take a look farther at my work. This one you can't actually solve. So this one would be extraneous. We won't have an answer from that one, but we do get a critical number from this one. So we stick it into our interval chart and we test using the first derivative test. And we're starting to notice that, okay, it goes in this kind of a shape and therefore you must have a minimum. Okay, so the increase is from -1 to infinity and the decrease is -infinity to -1. If you wanted to find the max, or sorry, not the max, the minimum, what you'd have to do is you'd have to take that -1, sub it back into your original equation, and then you'd get the y value. All right, and the very last one, determine again the interval and the intervals of increase and decrease and any local extrema. And so what we're going to do is we're going to take the derivative, blah, 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 set it equal to 0. If there's a denominator, you need to make sure that you test for the vertical asymptotes. So you need to find those vertical asymptotes because those are going to find their way into your interval chart. On the numerator, so looking purely at the numerator, we're then going to solve for any of your x-intercepts. And in this case, I probably needed quadratic formula, and so I got some decimal numbers. Those guys are also going to go into my interval chart. None of them should have the square brackets. So again, your interval chart is your first derivative test because you're testing to see what your first derivative positive and negatives will look like. And then that'll tell you about your overall function. So I have a max. There looks like there's some sort of an asymptote at 1, and then you have another max. Okay, so the increase and decrease regions are from negative infinity to negative 0.22 and 1.1 to 2.22 for the increase. Decrease is from negative 0.22 to 1, and then also 2.22 to infinity. And if you wanted, again, you could find those maximums and minimums by taking the x values here and subbing them into your original equation. Okay, so that is how taking the first derivative would be able to tell you some extra pieces of information about your overall function. So in the next video, we're going to talk about taking a second derivative.